Hi, everyone, and welcome to Chapter 15, Testing of Hypotheses, alternatively known as the last chapter we will be covering from our stats textbook. So if that is something that makes you do a happy dance, feel free to do that. But what I will say as we dive into this chapter is this is kind of a culmination of a lot of different topics that we've been talking about in class. And so we're going to see how these different statistical ideas converge in a way that really helps with decision making in the real world. That is what the testing of hypotheses is all about. So we're going to jump into section 15.1, which helps us figure out the lay of the land when it comes to what we mean by hypotheses in a statistical sense. And the easiest way to get at that is by talking through a very specific example. So in mining applications, it's often useful to take a large metal deposits that have been mined and melt them down to something known as an ingot. Now, an ingot is a huge piece of metal. It's been cast in a specific shape, and it's done in such a way that it's really useful for secondary applications of the metal. Now, what happens when ingots are cast is as the metal cools, there will sometimes be cracks that develop on the surface, and that's a bad thing. If you develop cracks, then that whole big chunk of metal needs to be melted down again and recast all over. So it's a time-consuming process to melt it down. The recasting is very costly. It wastes a lot of energy. And so that's something that companies want to avoid as far as possible. Now, most companies use a method known as direct chilling. In fact, 2/3 of aluminum producers use direct chilling for cooling these aluminum ingots. And if we focus in and look at one very specific aluminum plant, they have a track record of developing cracks in 20% of the ingots that they cast. So 20% of all their ingots have to be melted down and recast. The plant management sat down, had a discussion, talked to some scientists, made some adjustments to their machines in consultation with engineers, and they made some pretty big changes to their cooling procedure. And so after the cooling procedure, they took a sample of 400 ingots that have been cooled using this new method. And what they found is, after the changes in these 400 samples, only 17% of them developed cracks. Now, remember, their baseline here was this happened to 20% of samples. And so the question here is, has the method worked? These changes that they've implemented, does it actually represent an improvement? I know you may look at the numbers and say, oh yeah, sure, 17% is less than 20%, so things have improved. But remember, 17% here is a sample proportion, and we know that there is variability in a sample proportion. So are we looking at something that represents a real change? Has there been a real reduction? Are things really more efficient? Or does the 17% just represent typical variability? Like if the truth is still 20%, would it be very atypical to have a sample and observe 17% in the sample? How can we figure this out? So let's take this example and reformulate it as a statistical hypothesis testing problem. And whenever we are formulating statistical hypotheses, there will be two competing hypotheses. One of them we call the null hypothesis, The other one we call the alternative hypothesis. And the null hypothesis generally represents the status quo. The null hypothesis assumed that nothing has changed from what has previously been established. So the null hypothesis represents null change or no change. And so we also often write it as an H with a subscript 0. H0 or H0 for the null hypothesis. And the null hypothesis will generally be formulated as saying that a specific population parameter is equal to some hypothesized value. Let's make that a bit more concrete. In this example that we're talking through, the proportion of ingots that develop cracks, that's our P, right? That's our population proportion. We believe that the status quo has been maintained. That is our null hypothesis always. And the status quo was 20% develop cracks. So our null hypothesis says the population parameter, in this case, the population proportion, is equal to 20%. Nothing has changed. Status quo has been maintained. The alternative hypothesis is not a single value. The null hypothesis you saw was a specific value, 0.2 or 20%. The alternative hypothesis is not a single value, but is a collection of other values that could occur. You can think of it as a negation of the null hypothesis, because the null hypothesis and the alternative hypothesis cannot both be true. They cannot overlap in any way. So our alternative hypothesis says that population parameter, it is not equal to the hypothesized value. So in our example, the alternative hypothesis denoted HA, in this case, is that the population proportion P is no longer equal to the 20%. So not equal to means different from. So let me scroll back up so you can have the two side by side. The null hypothesis says P is equal to 0.2. The proportion is still 20%. The alternative says P is no longer equal to 0.2. It is now something different from 20%. And we are going to develop the statistical tools that help us determine which of these hypotheses is true. But the question we could ask right now is, how big a change or how small of a change will convince us that something has really happened? For example, say the new cracking rate wasn't 17%, but was 19.8%. Like, you would intuitively say to me, oh, well, 19.8%, that is really close to 20%. Like, it's really easy saying that's probably just sampling variability. At the same time, if the new cracking rate had been 1% as opposed to 20%, you would say to me, oh, that's a really big change. Definitely something has happened. Their method is improved because now it's only happening 1% of the time, really big shift away from 20%. So this is a change that is unlikely to be just attributable to random chance or to sampling variability. But the value in our example is kind of an in-between value, right? It's not so close to 20% that we immediately have this gut reaction of saying, oh, this is probably just noise. And it's not so far away that we can definitively say that something has happened. So if we have a sample of size 400, one of the things we can do is calculate the standard deviation, assuming that the null hypothesis is true. So remember, when the null hypothesis is true, we know that the value for the proportion is 20%. That means we can plug these values into our standard deviation formula, And in this case, we find that the standard deviation is 0.02 or 2%. Now, because our sample size is large, the central limit theorem applies. And so if we think about what our sampling distribution looks like, we can say, oh, the normal approximation holds because the sample size is large. And remember, this is attributable to the central limit theorem. So if we draw our sampling distribution, we can expect an approximate bell curve. It'll be centered at 20%. And then if we visualize our 68, 95, 99.7% rule, we have increments the size of the standard deviation, which in this case is 2%. So what this tells us is, even if the truth is 20%, it will still happen, say, 95% of the time that our sample proportion is somewhere between 16 and 24%. So a value of 17% is not that atypical because it's inside this middle 95%. Only 5% of the time will the value be more extreme, but the 17% is in the range of possibility. So how likely or unlikely is the 17%? Well, we can calculate this in a few different ways. One of them is by converting the 17% to a z-score, which is equivalent to saying, okay, let's look at the rate of 17%. How far is that from my null hypothesis value of 20%? Well, the difference is 3%. Our standard deviation is 2%, so we are 1.5 standard deviations away from the center of the distribution. So I can visualize my step size here. This is 1.5 standard deviations. And we could also take a step of 1.5 standard deviations in the other direction. So usually when we are evaluating a hypothesis, we'll often allow the evaluation to be done in such a way that we consider deviations in either direction. So in this case, we observe a 3% step in one direction, but we therefore also consider a 3% step in the other direction. And so we want to evaluate how likely or unlikely this is to happen. And that corresponds to taking this normal bell curve and figuring out what the chances are of having a value as extreme or more extreme. So having a value of 17% or smaller, which also corresponds to the chance of having a value of 23% or larger. And you've had some practice using the bell curve. We'll do some examples of this in our live session tomorrow, but this corresponds on each side to roughly 6.7%, which if we add the two tail chance numbers together, we end up pretty close to 13%. So if the truth happens to still be 20%, it will still happen 13% of the time that a sample of 400 will result in a sample proportion that is as far away or further away than the 17% is from the 20%. So I know that's a lot to take in. So what I might recommend at this point is rewind this video to the start of this example and listen through the whole example one more time. We're definitely going to look at multiple applications in our live session tomorrow, but I think this example is pretty central. And so I want you to make sure that you're putting together all these concepts: sampling distributions, bell curve, z-scores, standard deviations, all of those come into play here. What we conclude in this particular instance is if we take a sample of 400 ingots, then having a cracking rate as far away as 17% or even further away, that'll happen just by chance 13% of the time. The question is, does this seem very unusual? And I would say it depends. Like, is something unusual if it only happens 13% of the time? Would you go outside without an umbrella if there were only a 13% chance of rain? Versus, would you go outside if there were a 13% chance of a tornado? So 13%, in some sense, our evaluation of that is relative because it depends on the risk associated with it. And so that is why in a lot of these instances, we'll calculate a probability, but it is up to the person who asked for the analysis to determine whether they consider that an appropriate risk or not an appropriate risk, or whether they consider that chance small or large. I think a good way to contextualize this is to think of hypothesis testing as a criminal trial. So we start with the null hypothesis. The null hypothesis in a criminal trial is the presumption of innocence. You are assumed innocent until proven guilty. So then in the criminal trial, someone's going to present all this evidence. Oh, the police found the bank's money in the person's house. In fact, the person was sitting on their couch still wearing a mask that was seen at the robbery, and the getaway car was found in their driveway. So the jury then goes and deliberates. They talk through all these evidence and they ask themselves, how likely is the presumption of innocence? Is there a 1% chance the person is innocent? Is there a 5% chance they're innocent? Is there a 15% chance that they're innocent? And a jury, of course, has to determine this beyond a reasonable doubt. They don't use a probabilistic model. But in our context, we will usually rely in a specific application on an expert to define for us what unlikely means. So the way we end up doing this is through the calculation of p-values. Now, you'll have to pay attention here because we'll have sometimes still a p for a proportion, but now we'll also have a p for a p-value. Usually the p-value p will be hyphenated. So p on its own is going to represent a proportion, but you will also see p hyphen value for p-value. What is a p-value? A p-value is defined as the probability or the chance of observing data similar to the sample or more unusual or more unlikely than the sample, given that the null hypothesis is true. So that's a mouthful. Take a moment and read through that definition again. I'm going to do my best now to illustrate to you exactly what that definition means. But what we are trying to do is assign a number to how surprised we are by our results if the null hypothesis is true. So if we calculate a p-value and it's a very low number, a very low p-value will tell us either that the null hypothesis is not true or that something remarkable has occurred. A low p-value will result in us rejecting the null hypothesis. On the other hand, if our p-value is high, that tells us there is nothing surprising going on. The data are consistent with the model as specified by the null hypothesis, and we therefore do not reject the null hypothesis. What does it mean if we ask whether the data are consistent with the null hypothesis or not? Well, here I have two illustrations. In both instances, the bell curve represents the distribution we would expect to see if the null hypothesis were true, and then the red dots represent the data points. So in the first example, you can see the data lie all along the bell curve. So the data seem to be consistent. The data are not deviating from the bell curve because they span the bell curve pretty well. So the data line up with our expectations. So here we would expect a large p-value because the data and the null hypothesis appear consistent with one another. But in the second graph here, the data are not consistent with the null hypothesis. What do I mean by that? Well, the data do not span the entire bell curve. Here on the left, there's nothing going on. So our data don't fully line up with what we expect to see if the null hypothesis were true. And so in this instance, we would expect a small p-value because the data do not line up with the null hypothesis completely. So that's the general idea. If I stick with this courtroom analogy for a minute, if we're looking at evaluating evidence, the defendant is either guilty or not guilty. If the defendant is guilty, it's because the p-value is very small and the evidence is clear. If the p-value is not small, the defendant is not guilty. Now, this is not the same thing as saying that the defendant is innocent. The defendant could be innocent or could be guilty, but there was not enough evidence to convict. And so this parallels how we write our conclusions for hypothesis testing. We never say that we accept the null hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis, but we never say that we accept. So I think this slide just talks you through some more of how we formulate our statements around the null hypothesis, but know that we always talk about the null. We never say if we reach a conclusion about the alternative. We always say what our conclusion is in terms of the null hypothesis. So you're going to reach a conclusion in terms of the null hypothesis. You will either reject it or you will not reject it. And if you don't reject it, that doesn't mean that it's false. It just means that you had insufficient evidence. For example, perhaps my null hypothesis, this is a bit of a silly example, but I hope it illustrates it. Maybe my null hypothesis is that all toothpaste contains mint. So I make sure I get a sample of 100 different kinds of toothpaste, and I find that each tube in my sample contains mint. Does that mean that there is no toothpaste out there that doesn't contain mint? No, it does not. My sample just didn't find any, so there was insufficient evidence to reject my null hypothesis. So we'll talk through this a little bit more in our live session tomorrow, but when we formulate our alternative, the earlier example we talked about said it was a complete contradiction. We looked at either side of the middle value of 20%. So the alternative said any value that's not 20%. But there is a different way of formulating an alternative. Sometimes you specifically want to detect a decrease. So you formulate your alternative as saying you only care about the value being less than 20%. Or maybe you were only interested in detecting an increase, which would correspond to an alternative of saying P is greater than 20%. So there are ways of formulating one-sided alternatives. And again, we'll dig in tomorrow and do some examples of this. So your alternatives, if they're one-sided, are formulated using either a less than or a greater than, if it's important to specifically test for a decrease or an increase in the quantity. Whereas if you have a two-sided alternative, you're testing for either an increase or a decrease. You don't care which. You just care that there's been some change from the value under the null hypothesis. Now, there is one really nice advantage to two-sided p-values, and that is the conclusion you reach with those will always be the same as the conclusion you reach from constructing a confidence interval. So there is a connection between confidence intervals and hypothesis testing. But I know I've been rambling for a while here, so I'm going to call it quits for today, and I will see all of you in our next live Zoom session.